A deeper theory of how reality, of how space and time works. Black holes are interesting because we have a place called the event horizon where we think that we have full control of the physics. We understand what's happening, but there is a fundamental clash between our two basic theories of nature, both quantum theory and general relativity together. Supernova explosion. So this is an island. There are 100,000 million, perhaps 200,000 million, stars like our Sun. There are perhaps 1 billion stars in the center of this galaxy, shining brightly. This looks like a star that must be closer to us than that galaxy because it's so bright. It actually isn't. It's actually something called a supernova explosion. This is a star in the galaxy. It's on the edge of the galaxy. It's the same distance away as the billion or so suns in the center, and the 100 billion or so stars in the disk, same distance away. But it's glowing as brightly as 1 billion suns. How could that be? One star glowing as brightly as 1 billion? Well, it's something called a supernova explosion, the death of a massive star. But it's actually a very interesting one. What we think that is, it's called a Type 1a supernova. It's something called a white dwarf. So that's the ultimate fate of the Sun. It's a star that's burned out all its fuel and is just sitting there in space, gradually fading away. But it's a white dwarf that had a companion star orbiting around it. Now, the white dwarf, the dying star, sucks matter off the companion star until it gets too big to support itself, too massive to support itself. And then it collapses, and it explodes. We know that process very well. It was a process that was predicted, actually, from quantum mechanics, from our theory of atoms and molecules, back in the 1930s. So it's a very specific process, and we can calculate precisely how brightly that explosion should be because we understand the mechanism beautifully. So we know how bright that is. We know how bright it looks because we've taken a picture of it. So we can work out how far it is away. And this is the second bit of evidence you need. So we've got two things now. We've got that you look out into the sky, and you see that things are speeding away from us because you can measure the shift in the light. And we know exactly how far those things are because we can look for things like these supernova explosions in the distant galaxies. Now, these are rare. You get, on average, about 1 supernova per century per galaxy. So very rare. But there are a lot of galaxies. Supernovae in hundreds of galaxies have been measured, and we've made a map of the universe. We've got the distant galaxies. We know how far away they are. We know how fast they're receding. Antimatter asymmetry. Modern physics has given us a glimpse of what the true nature of the universe is. There is still so much more to explore. One big mystery in science today is the matter-antimatter asymmetry problem. But to better understand this complex issue, we have to grasp the nature of antimatter. CERN has managed to capture atoms of antimatter hydrogen. Now, antimatter, I should say, gets made all the time. It gets made in these cosmic ray collisions. We've been using it for years in particle physics experiments, but we've never been able to build atoms of it, so get an antiproton and put an anti-electron in orbit around the proton for any length of time. So the great advance is that we've worked out how to do that. And that's interesting because once you've got a hydrogen atom is the best understood, probably the best understood system in the universe. We understand how hydrogen atoms work with extremely high precision because they're very, very simple. So by building anti-hydrogen atoms, we can look in detail at the way the differences in behavior, if there are any differences, between matter and antimatter. And that's an enormous question because we don't know whether they behave in precisely the same way or whether there are tiny differences. We think there may be tiny differences because we need to explain why there isn't really very much antimatter in the universe today when it was probably made. Well, it must have been made, in equal amounts at the Big Bang. So that's a big question. Could it be dark matter? So that matters. The other great question, which is a bit more, perhaps, a bit easier to see that we might get an answer to, is that another 25 to 26% of the universe is made up of something called dark matter. There's a lot of stuff we can't see, and we don't know what it is. And it's something like 96% of the universe. So that's kind of a bit embarrassing in a complete theory of the universe. Some of it, we think, is in the form of dark matter. We don't think, we're very sure, actually, that it isn't antimatter because you'd see it bumping into matter and giving out lots of energy and light. And we don't see that, so we think it might be something else. It must be something else. And we think there are certain kinds of particles we think we might find at the Large Hadron Collider, which are very strong candidates for that. So it's not dark matter, but it's interesting because we want to see if there are differences in behavior between antimatter and matter. At CERN, physicists make antimatter to study and experiment. Large Hadron Collider. The starting point is the antiproton decelerator, which slows down antiprotons so that physicists can investigate their properties. Scientists are also eagerly waiting for other experiments at the Large Hadron Collider, particularly the discovery of new particles, which will hopefully give us a better understanding of our universe. This is why there's tremendous excitement now at the LHC. There are hints of interesting particles, a particular one, what we call around 750 GeV, 750 times the mass of the proton, which is a signal that is not statistically significant enough. As we saw in the supernova results, actually, the dark energy results, not significant enough yet. Large Hadron Collider. Need more data. That's why the LHC is running now, to take it. But those signals have caused already just preliminary results that may go away with more data. And I don't know, because we're analyzing the data, so I don't have any secret knowledge I'm hiding away. But if it's there, it would be a heavy particle, a new heavy particle 750 times the mass of the proton, decaying into 2 photons, 2 particles of light. That's what it would be. If the signal stands up, it could be one of the particles for dark matter. Could be one of those. Could be, though, if you go more speculative and exciting, it's one of the signatures for extra dimensions in the universe, so-called collusion graviton signals. There are ideas around that. So it could be that at LHC, we're on the verge of making a breakthrough. But that's the key, the points of the Large Hadron Collider. It was built because we knew we could confirm or deny the Higgs model. But it was also built because it's operating in an energy regime in which we've never operated before. So it is certainly not ruled out that there is new physics in that energy regime. While physicists can confidently say what happened. Dark matter. A billionth of a second after the Big Bang, the vast majority of the universe remains unknown. In fact, we only understand about 5% of the total composition of the universe, which is ordinary matter. The other 95%, which consists of dark matter and dark energy, remains in the realm of unexplained cosmic phenomena. So we look into the universe, and we see that there's a lot of stuff there that's interacting gravitationally but is not interacting strongly with the matter out of which we are made and the stars are made. It's almost certain that that's some form of particle that fits beautifully. And we see lots of different observations, the way galaxies rotate and interact, and even the oldest light in the universe, the so-called cosmic microwave background radiation. We see the signature of that stuff in that light as well. So we think that there's some other particle out there. And to be honest, we thought we would have detected it, I think, at LHC. We have lots of theories called supersymmetric theories that make predictions for all sorts of different particles that would interact weakly with normal matter. I think it's broadly seen as a surprise that we haven't seen them at LHC. So that just may well mean that either they're a bit too massive, so we need more energy to make them, and we just haven't quite got enough, or we're not making enough of them often enough to see them. So we also look for them, by the way, directly. So we have experiments on the mountains, and we're looking for the rare occasions when these dark matter particles bump into the particles of matter in the detector. The galaxy is swimming with dark matter as far as we can tell, but it interacts very weakly with this matter, so it doesn't bump into us very often. So we're looking for the direct detection of it. So it's 5 times as much matter as dark matter than is normal matter. Then the number is 25% of the universe. So, roughly speaking, about 5% of the universe is normal matter, the stars. 5% is normal matter, about 25% is dark matter, and about 70% is dark energy. So Einstein's theory, which works spectacularly well, says that if you put stuff into the universe, as we said before, then it warps and deforms and stretches. And it very precisely tells you, Given the stuff that you put in it, how much does it stretch, and how does it stretch? The thing we observe is how the universe is expanding, and how that expansion rate is changing, and how it's changed over time. So we have very precise measurements of that. So then we can use the theory to tell us what's in it, given that we know how it's responding to that stuff. And that's how we discovered dark energy. So we noticed that the universe's expansion rate is increasing. So the universe is accelerating in its expansion, which is exactly the opposite of what we thought. Conclusion. Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this.